Good afternoon, folks. How are you today? We are in second part of Lab 6. In the first part, we learned about isothermal transformation in eutectoid steel. Isothermal means constant temperature, where the transformations occur over a constant temperature. Then we also learned what happens when we continuously cool these eutectoid steels. And we learned about continuous cooled transformation diagrams. Now in this part, we are going to learn about hardenability of steels, and we are going to conduct the Jominy End-Quench test on two different steels. So let's quickly review isothermal transformations. We are talking about eutectoid steel. You know, at above the eutectoid temperature, the steel is all austenite. And now when we quench the steel below eutectoid temperatures, there are basically three things that can happen. If we do the isothermal transformation above the nose temperature, we get all pearlite. Below the nose temperature, we get bainite. In between martensite start and finish temperature, if we quench it to those temperature, we'll get a combination of austenite and martensite. And of course, if we cool it below martensite finish temperature, we'll get all 100% martensite. So we have three things that can happen. Austenite, when cooled, can become pearlite. Below nose temperatures, it can become bainite. And of course, below martensite finish temperature, it becomes martensite. Then we looked at continuous cool diagrams where these pearlite start and pearlite finish curve move slightly down and to the right. And we found we have two critical cooling rates, this red cooling rate and the blue cooling rate. So as we change the cooling rates, our transformation can produce all martensite or a combination of martensite and pearlite or all pearlite. But the key idea here is depending on the cooling rate, as we go to the right, we get martensite or martensite plus pearlite or all pearlite. As we go to the right, basically material is becoming softer. Or if we go to the left, it is becoming harder. That's the idea. Because we know martensite is very hard. So if we use very fast cooling rates, we get very hard structure. Medium cooling rates, we get a combination, we get a medium hard structure. If we use slow cooling rate, we get all pearlite, and that's a soft structure. Now remember that it is not just that it is all the same hardness. As we decrease the cooling rate, notice the nature of pearlite is also changing. It is going from fine to coarse, so it is becoming software. So as we go to the right on the scale, as we slow down the cooling rates, we also result in softer structures. And of course, we know that as hardness goes up, which signifies strength goes up, and the price we pay is in terms of ductility and toughness, right? So that was all for eutectoid steels. So now let's talk about this concept of hardenability. So hardenability is the ability to harden by formation of martensite. So if we can form martensite, we know our structure becomes harder. So a low hardening Low hardenability steel is one when on quenching austenite, martensite falls only on a skin, shallow depth. So these are called shallow hardening steels. So when we look at our transformation curves, what that means is, remember, our first critical cooling rate was like this, and we formed all martensite. So if we can move this curve to the right, that means martensite will form even on slower cooling rates. We will have greater hardenability. So the farther the C curve is to the right, higher hardenability we have. We say it is easier to form martensite. So a higher hardenability steel, therefore, on quenching of austenite, martensite will form at a greater depth. So these are called true or deep hardening steels. So our left critical cooling rate becomes even slower. So of course, carbon content has an effect on hardenability. It turns out that eutectoid steel has the highest hardenability. So if eutectoid steel means 0.76% carbon. So as we move away from this 0.76% carbon, whether we move to the left, lower carbon, the more to the left we move, the more the C curve moves to the left. So lower hardenability. If we increase the carbon percentage from 0.76, again the curve moves to the left and hardenability decreases. So let's see what happens in a hypoeutectoid steel. So in the last lab, what we did was we did slow cooling. So here is hypoeutectoid steel. At point C, we had 100% austenite. Then at point right above the eutectoid, we had a combination of austenite, which had not transformed, and pro-eutectoid alpha. So this pro-eutectoid alpha stays even when we cool it below the eutectoid temperature, but the austenite becomes pearlite. So let's see what happens when we continuously cool this steel. So when we continuously cool this, what we have is we will have a ferrite start curve, because remember, as we go cool through, we will have ferrite forming. And then once we reach eutectoid temperature, then the pearlite, etc., will begin to form. So also notice the C curve has moved so much that it is almost touching the y-axis. So that means it will be very difficult to form 100% martensite unless we quench it so fast that we never touch this blue curve. So anyway, this blue curve is ferrite start curve. We have pearlite start curve, bainite start. This blue is bainite, yellow is bainite start. And then we have, of course, pearlite finish, bainite finish, martensite start temperature, and somewhere here is martensite finish temperature. So we have a number of critical cooling rates. First critical cooling rate just misses the bainite start curve. So in this region, we will form ferrite plus martensite. So as we slow down the cooling rates, this is the kind of structures that can form. We can have pro-eutectoid ferrite plus martensite. Very soft, very hard. If we cool it slower, ferrite plus bainite plus martensite. So you can see I'm just reading it from left to right here. If we cool slower rate, ferrite plus bainite plus pearlite plus martensite. And then, of course, notice there is this critical cooling rate where we just hit the Bainite finish curve. So when we hit the Bainite finish curve, we will just form Bainite and perlite. Then we have this, the slowest cooling curve, 2 degrees per second, which misses but cuts perlite finish. So we will have, so as we go down here, slower cooling rates. But also the material is becoming softer, right? Okay, so you can see the key idea here is by cooling our steel at a different cooling rate, we can customize combination of hardness and toughness. So whatever hardness we want, we can control it by controlling the cooling rate. Now, what happens if we add alloying elements? Alloying elements such as chromium, nickel, molybdenum, tungsten, they cause significant changes in position and shapes of these transformation curves. So they can really modify these things quite a bit. So they can shift the nose of the perlite transformation curve to the right. That means increase the hardenability. They may also cause separation of a bainite nose, different from a perlite nose. So let's see an example. So here is a 4340 steel. We'll talk about the composition later on because we are going to test it. But again, notice it has also 0.40% carbon. But here you can see what has happened is these are the isothermal transformation diagrams. And you can see perlite start, perlite finish, bainite start, bainite finish. So perlite has its own C curve instead of just the top half, and bainite has its own C curve instead of just the bottom half. But now when we go to continuous cooling diagrams, remember in continuous cooling, we are not going to see some of these curves. So we just see these curves and they are marked. But the key idea here is, again, notice as we go from left to right, now in this particular case, since our ferrite start and bainite start curves were shifted to the right because of all those alloying elements, we can now form martensite. In fact, we can form martensite for a range of cooling rates. So you can see we can form martensite to great depth. Notice this compared to here we could not form 100% martensite at all, right? Plain carbon steel. So this is an example of high hardenability steel. So how do we measure hardenability? We have a very clever way to measure hardenability. So what we do is we have a sample that has got a standard size. It is 1 inch in diameter, 4 inch in length. And what we do is we drill a small hole so we can put a cap on top of it. And then we have a jet, water jet, so that when the sample is not there, it has a standard height. And you will see this. So this water sprays at this end. So this particular bar is first austenized. It is taken to a high temperature so that it is 100% austenite. And then we transfer it directly from the furnace into this kind of a fixture where it hangs from some kind of a support over this water jet. So that means that this particular end is experiencing water quenching, the fastest cooling. On the other hand, this end is undergoing air cooling. So from here to here, we have cooling rates varying from water quenching to air cool. So obviously different cooling rates are going to produce different structures. So if we measure hardness from the quenched end to the other end, we can figure out what kind of structures are forming in different layers. So what we will do, big picture, we are going to take our specimen, put it in the furnace, heat it up with the hat and everything. We will have our Jominy End-Quench setup ready. And then we are going to take the specimen out, hang it over here, and it'll begin to cool. Once the specimen is at room temperature, we take it out of this fixture. We will grind a flat and measure the hardness from the quenched end on the surface. And we are going to plot it. So what is happening here? If this is our quenched end, this undergoes fastest cooling. So you can see it can form martensite. Farther away, it can form martensite and perlite. Yet farther away, it will form slowest cooling rate. It will form all perlite. So of course, we are going to have different hardnesses. And this is our hardness profile, this red curve. So this red curve is a plot of hardness versus distance from the quenched end. So these are the different hardenability curves we might see. So 1040 steel we see doesn't have much hardenability. The hardness goes down very quickly. On the other hand, 4340 steel you can see remains hard for sufficient depth. So 1040 is a low hardenability steel and 4340 is a high hardenability steel. So this is what we are hopefully going to find. Let's see our procedures. So we have our specimen, and what we are going to do is we have put it in the furnace. While it is in the furnace, let's see how we are going to prep up our machine, our Jominy End-Quench test.
Before we put the specimens into the quenching unit, we need to ensure that the jet is set appropriately according to the ASTM standard, so that the jet will hit the bottom of the specimen and come out horizontally so that it only wets the bottom, does not wet the sides of the specimen at all. So to do that, I need to ensure that the jet is approximately 2 inches high. So I'll put this ruler into the place where the specimen would be, rest it on the edge of the jet, and turn the jet on. And that jet is, well, it's fluctuating, but it seems to be averaging just a hair over 2.5 inches, or over 2 inches, not 2.5. So I'm going to adjust it very slightly. And that looks like we have a winner. So now we're ready to put the specimens into the tester quencher. So specimens have been in the oven at 850 degrees C for about an hour. So they're a nice uniform temperature. When I open the oven, you'll get to see the color that 850 degrees C is. I have a pair of heavy-duty tongs specifically for lifting these specimens out. So here we go. Grab the specimen. Drop it into the quencher and start the water. You can see how the bottom of the bar almost immediately turns a dull gray brown, but the top of the bar is still glowing. And that very clearly illustrates the difference in the cooling rates from the bottom of the bar to the top of the bar. And as it cools, the top is glowing a more dull red color, and the brown is slowly spreading up along the length of the bar.
Okay, now that we have cooled our specimen, next thing we are going to do is we are going to grind flats on the two sides of the sample. Now we don't have a decent grinding setup. So instead of grinding, what we are going to do is we are going to machine two flats. And here is Professor Humphrey showing that to you.
So this is the setup and the milling process to put the flat surfaces onto our specimens after they've been quenched so that we can measure Rockwell hardness along the length of the bar. We have a parallel in the vise there to support the specimen. I'm just tapping down on it there to make sure it's resting firmly against that parallel. Now we need to make sure that the specimen is centered under the end mill so that we get a good surface finish. And now I'm going to bring the end of the bar under the mill and do a touch off where we slowly raise the specimen up until we first see the end mill start to cut. And we'll set that as our 0 point. And now that I've got that 0 point, then I will raise it up between 15 and 18 thousandths of an inch so that we can remove just enough material to get a nice wide enough flat surface. The goal here, of course, is to just move the specimen under the end mill smoothly and slowly so that we get a nice surface finish. Again, the ASTM standard calls for the surface here to be ground rather than milled, but since we don't have a convenient setup in our machine shop to do that, then we make use of the end mill and we just do our best to get a nice clean surface. All right. And you can see the first surface, lay the specimen back in there, and we're resting the specimen on that flat so that we guarantee that the second flat is automatically parallel to the first one. So we just need to be careful clamping it in the vise that it doesn't roll. Tap on it just to make sure it's firmly in contact with the support underneath it. And we raise the work table another 15 to 18 thousandths of an inch, and we go back the other way and mill the second flat. You can see the hole at the end of the specimen, so this is the unquenched end, and now I'm moving toward the quenched end. Once we hit the end, we can speed up, shut off the mill, release the specimen, clean up all the chips. We don't want to get a chip under the specimen, between the specimen and the support, and there's our finished product.
Okay, now that we have machined flats on the two sides of this cooled specimen, we are going to now put it in a fixture so that we can make Rockwell hardness measurements at equidistance spots. So here is a very special fixture, and Professor Humphrey is going to explain what this is all about.
So we're back to using our Rockwell hardness tester. We have a special stage installed for doing the hardness tests on our bar that's been quenched on one end. All right, we can see the threaded hole on the other. We've machined a flat This is a very slight deviation from the ASTM standard. The ASTM standard says that this flat should be ground. We don't have a convenient way to do that, so we machine it and just get the best surface finish that we can. So the bar, we have two flats, so the bar rests on one. I'm just going to pick the one with the better surface finish to be the side we do our testing on. So the bar rests on one flat. All right, and then this clamp just holds the bar in place. So I press the bar against this screw on the end. And now I'll raise it up to the point where I can see the reflection of the indenter tip. All right, I want to get within about 1 millimeter of the surface so that I can see the reflection of the indenter tip. But I don't want to actually touch the surface. Now I'm going to use this screw on the right, and I'm going to use that to adjust the end of the bar to set the 0 point. And I want to get it so that the indenter and its reflection basically match. All right, so that the indenter tip is right at the end of the bar. Okay, so we've got the indenter tip lined up exactly with the end of the bar. This is important because for one of our specimens, the layer of martensite at the quenched end is going to be fairly thin. So if we don't get the 0 set well, then that's going to throw off all of our other measurements. Now if we look to the right, we'll see the micrometer knob. This is used for positioning the specimen. So right now it is set for 0, and it's marked in increments of 1/1000th of an inch, and it's 25 thousandths of an inch per complete revolution. So for ease of convenience during our experiment, I've had another minor deviation from the ASTM standard. We're not measuring at the exact locations prescribed by the ASTM standard. They're very slightly off, and I've just modified them so that they are increments of 25 thousandths of an inch. So it's 1 whole revolution or 2 whole revolutions distance between our measurement points.
Okay, so we are going to start measuring hardness along our specimen. Now, if this was eutectoid steel, of course, we are going to see a curve something like this, because we go from all martensite to all pearlite. So our hardness is going to continually decrease as pearlite becomes coarser and coarser. So here is again Professor Humphrey making the measurements. Now he had a long video, and of course I'm going to cut it short instead of looking at all the measurements.
Now we have our bar installed, the 0 point set. So this is the 1045 bar. So on our data sheet, we're just going to follow the list of locations printed on the data sheet. They're in multiples of 25 thousandths, again, 1 complete revolution of the micrometer. So our first measurement is at 50 thousandths. So that is 1, 2 revolutions of the bar. Procedure for making the measurement is the same as always. Use the handles to raise the platform up until the indenter makes contact, and then slowly raise, watching the LED at the top of the panel, stopping when we reach the green set LED. So our first measurement is 55.3. Lower the specimen just enough so that the indenter is no longer in contact, and now we can move the specimen to the second location, which is 100.1 thousandths, and so that is another 2 revolutions. 1, 2, and we repeat the measurement. 52.4. And lower the specimen. The first two measurements are 2 revolutions apart. The next several are 3 revolutions apart. Then we go to 5 and finally 10 revolutions. That's marked on the bottom of the data sheet. Also, whenever we get 2 measurements that are below 20 in a row, we can stop. If you look at the figure in the presentation, right, the hardenability curve basically ends when the hardness drops to a Rockwell C value of 20. So now we have 3 revolutions. And our next measurement. .0. You can see that the 1045, the hardness drops very rapidly. Next measurement is 0.25. That is also 3 revolutions. 1, 2, 3. .1. 1, 2, 3 revolutions. .3. Next location is 0.4. That's also 3 revolutions. 1, 2, 3. .4. Next is 0.475, which is again 3 revolutions. 1, 2, 3. Repeat the measurement. .8. Next is 0.55, which is still 3 revolutions. 1, 2, 3. .9. 3 more revolutions. All right, the data points are all 3 revolutions apart until we get to 1 full inch. And 19.9. That is a second data point in a row below 20. And so we are done testing this bar. So I'm going to remove the bar, and you can see both from the surface finish, at the end it's shinier, and you can see, if you look close up, that the indents for the first two are much smaller, indicating that we have a much harder material here. So our martensite layer is very thin, and then the hardness drops very rapidly as the quenching process, cooling process, formed bainite and pearlite, mostly pearlite, instead of martensite. So we're finished with this specimen, and we're ready to move on to our 4340 specimen. So here's our 4340 bar with the flats machined. All right, I can see the 43 stamped in the end to indicate that this is our 4340 specimen. So I'm going to load it into the specimen holder, same as before. I'm going to back this screw off a little bit, raise it up until the indenter is within a millimeter or so of the surface. And then I will use the indenter and its reflection, looking right along the end of the bar, to position the end of the bar to be exactly in line with the specimen. I've already set the micrometer back to 0, and so we're ready to begin. So I advance the micrometer 2 revolutions. 1, 2. That gets us to our first measurement point of 0.05 inches. .5.
Okay, so you saw Professor Humphrey making the measurements on our two samples, a plain carbon steel like 1045, and then he had just begun making measurements on 4340. So we are going to cover that all in our next part. But I want you to appreciate that there is going to be sample to sample scatter. So we won't be able to exactly reproduce a curve as you might find in a handbook. So there will always be a band of hardness values. Okay.